Hello, we're going to do another practice problem. Today is 10.4. This problem says here, for the beam and loading shown, use the double integration method to determine the equation of the elastic curve for segment AB of the beam. And we need to find the deflection at B, the slope at A, and we need to assume that the modulus elasticity and moment of inertia are a constant for the beam. So, quick note, chapter 10, what we're talking about is deflection of a beam. And so if we're deflecting, and we have our loading here, we're going to move in the y direction, right? Our beam is going to, as we can look at our beam and just through observation, we can deflect, we're going to deflect at B down, so negative y, right? So some notation, you'll see delta y is deflection, or in some textbooks they use lowercase delta, which that's supposed to be a lowercase delta. And this textbook that we're using right now, they're using nu, right? That's a nu. It looks like a V. So note that all of these are the same. So do not confuse nu with shear, which I have done in the past. Believe me, it will make your life difficult and your instructors will think you're not paying attention. So to follow the textbook, we're going to use nu, and this is deflection. And if we take the derivative of deflection, our nu, with respect to x, we get our slope. And if we take the derivative of slope, which is the double derivative of deflection, we get our moment, all with respect to x. So in this problem, let me draw real quick our little diagram here. If I have a loading acting down here of P at exactly halfway, so this is L over 2, and this is L over 2, then my reactions here are going to be P over 2 at A and P over 2 at C. So what we'll do is then I'm going to make an arbitrary cut because we're going to analyze between A and B. I'll make an arbitrary cut, and then I'll just draw a free body diagram with my shear, again, not to be confused with nu, which is deflection, and my moment, my reaction at A, and then our distance x. So summing the moments about our shear point equaling 0, identify the positive direction, and so then we get our moment to equal P over 2 multiplied to x. This is my moment equation. So now with my moment, what we can do is identify what my slope is, and then what my deflection is, just by integrating this equation. So if we integrate this equation, so integrate both sides, we get, we'll just use the notation that we had before. So our moment, which is this notation here, right? So integrating that, we get d nu dx equals, integrating p over 2 multiplied to x is going to become p over 4 multiplied to x squared. And then since we are not integrating on a certain identified bounds, we need to add our constant of integration. And so then integrating again, and this here is our slope equation, right? So slope. Integrating again, we get our deflection equals p over, and then this would become x cubed. 3 multiplied to 4 is 12, so this would be p over 12 x cubed plus c sub 1 multiplied to x plus another constant of integration, which would be c sub 2. So the next thing we need to talk about, this is, well, real quick, this is our deflection equation. So the next thing I want to mention is our boundary conditions, right? So boundary conditions, okay? And if you look at our member, you look at this beam, and we already talked about it, if we have a loading that's going to act right dead center on this, right at midspan, it's going to deflect this beam like this, right? We're going to have it's going to make it look like a smiley face, okay? So at the support conditions here, right, there's a couple of things happening, and right here at midspan, there's something happening. So at the support conditions, if it's supported there, that means that there's no delta y, right? So if there's no movement here at this point, that means that we can say our deflection at the support conditions equals 0. And our slope here is going to have a value because it's with the horizontal, there's an angle here, which is theta. But as we move closer and closer to midspan, that angle theta decreases to a point where right at midspan, our slope equals 0. So I recommend, if you haven't already, read the conditions, the boundary conditions out of the textbook and become familiar with what is occurring where in the member. So, but here, let's note that deflection is 0 when x is 0, so talking about point A, and our slope is 0 when x equals L over 2, which is halfway, okay? So noting that, we can use this information and plug it into the equations that we already solved for, right, and determine what our constants of integration are. So for the first one, we can substitute, let's just picking one, we'll do the first two down here. When our slope is 0, x is L over 2. So I'm going to pick this equation here, which is our slope equation, and say, well, 0 equals p over 4 multiplied to L over 2 squared plus c sub 1. So this becomes L squared over 4, 4 times 4 is 16. Moving this over to the other side, we get c sub 1 equals negative pl squared over 16. Okay, and that's the first constant. And so then plugging x equals 0 into our deflection equation, and deflection equals 0, we get 0 equals p over 12 multiplied to 0 cubed plus c sub 1 multiplied to 0 plus c sub 2, and then just analyzing that all of this goes to 0, c sub 2 equals 0. Okay? So our equation then, or our constants of integration are then solved for. We know what they are. So then we can find our elastic curve equation, right? So our deflection then, we can say E sub I, or EI, our modulus of elasticity, moment of inertia, multiplied to deflection, is going to equal P over 12 x cubed plus, or I apologize, minus, because I'm using our deflection equation here, minus PL squared over 16 multiplied to x. Now in our textbook, they're going to want you, this is technically the right answer, but in our textbook, what they want you to do is do some algebraic manipulation. So Wiley Plus might want you to do this as well. Just note that the actual deflection will be, you need to move E and I over, so modulus of elasticity and our moment of inertia need to be moved over, and reduce this down as much as possible, but you should end up with a negative px over 48 EI multiplied to 3L squared minus 4x squared. And this is the deflection equation right here, okay? So the next equation, what we'll do, and remind you that this equation is only valid between A and B, right? Because that's what we're analyzing. So the equation, if we were going to move forward and analyze between B and C, then we would need to come up with another equation because our loading conditions changed. Okay, so note that. That's important. This does not work for the entire member. This is only valid when x is between 0 and L over 2. Okay, so now that we have this, we need to determine what is the deflection at B, right? So our deflection at B is going to equal, we're just going to plug in what the value is at B, what x is at B, which is L over 2. So just plug that in and solve. Plug and chug at this point. So L over 2 over 48 EI multiplied to 3L squared minus 4 L over 2 squared. And this is, again, the right answer, but you still need to reduce it down algebraically. And this becomes deflection at B equals negative PL cubed over 48 EI. And then this is the correct answer for part B. So now part C, which we want to find the slope at A. So let me go back up to our problem statement real quick. So it says here, find the slope at A. So we determined, there's going to be a slope here at A, but looking at our equations that I was solving for earlier, this is my slope equation, which is the derivative of our deflection equation. So I'm going to use this equation here, the slope, and say the derivative of slope with respect to x at point A is going to equal theta at A, which equals P multiplied to 0 squared over 4 plus C, which is our constant of integration. We determined that earlier, which is actually negative. A negative PL squared over 16 EI. And then obviously this just goes to 0, and our slope at A is going to equal negative PL squared over 16 EI. And that is part C.